55 years ago, Neil Armstrong and Buzz Aldrin became the first people to set foot on the moon, and along with Michael Collins, rode Apollo 11 back to Earth and opened the road from Earth to the stars in the hearts of the 650 million people who witnessed the landing and the rest of us who were born after. While Neil Armstrong and Michael Collins are no longer with us, at age 95, General Aldrin remains a living legend, and the work of all three Apollo 11 astronauts will be remembered for ages to come. But Aldrin's work to help with space neither began nor ended with that mission. He is a governor of the National Space Society, and for many of our long-term members he is family, a fellow advocate and scientist working to pave that road to space, who has developed many projects and led many efforts to help with that goal. We'll be focusing on one of those projects today, the Mars Cycler craft, better known now as an Aldrin Cycler, a spacecraft able to carry large cargoes back and forth to Earth cheaply and safely. I think it's easy for Buzz's work as a scientist and engineer to get overshadowed by that historic mission. After graduating from West Point in 1951 with a degree in mechanical engineering, he would go on to fly 66 combat missions during the Korean War, before completing his doctorate in 1963 from MIT. His doctoral thesis was already on a space bent, line-of-sight guidance techniques for manned orbital rendezvous, and the Air Force then assigned him to Project Gemini. He and Jim Lovell went on to fly the Gemini 12 mission in 1966, and both would later serve in the Apollo missions, with Lovell being the commander of the fateful Apollo 13 mission. Notably, during that final Gemini mission, it was Aldrin who navigated to the Agena target vehicle when their computer broke down, using a sextant and a pencil, and who performed the first completely successful spacewalk, succeeding a series of tasks deemed critical for the Apollo mission to move forward. If he had never done another thing for space exploration and development, his position in space history would have been forever secure. But as mentioned, he has been very active in the space community afterwards, again including his role as a longtime governor of the National Space Society, which I have the honor of serving as president of, and the Mars Society Steering Committee. And speaking of Mars, in 1985 he would develop a spacecraft trajectory known as the Aldrin Cycler, and he would work with others to develop the concept and publish papers on it and some related alternatives. But what is it? Simply put, a cycler craft, sometimes called a cycler castle because of their implied role and purpose, which is to simply act as a ferry craft back and forth between cislunar space and Mars orbit. Once you build one, or a pair of them, and put them in the orbital pattern, they can loop past Earth and Mars over and over again without needing to spend any more fuel themselves. Except maybe a little for minor course corrections, though there are powered versions we'll also look at today. This means they can carry a huge amount of shielding, along with tons of other equipment needed for the crew during the voyage between planets, but not on the planet. Thus, you can send a light shuttle up with a crew for a mission without all the bulky radiation shielding and without needing to carry tons of water or air or the equipment to recycle or clean them. The Cycler Castle is well stocked for its long siege by radiation, micrometeors, and the vacuum of space. While we would expect early cyclers to be fairly bare bones, later stage ones could get away with rotating sections for spin gravity, using water reserves for keeping fish and algae for food, and even a swimming pool, and growing a steady supply of fresh produce to help recycle carbon dioxide and give the crew some green space too. When you arrive at Mars, your smaller ship then exits, flies down to Mars, or to a space station over Mars, and proceeds with its mission there. Ideally, after the first mission or two, you have nuclear reactors and air, water, and fuel production down on Mars to replenish fuel for the return flight to orbit some months later. And if you are only using one cycler, it will be quite a few months. There's also no reason that cyclers themselves might not have reactors as power sources, and such a craft could harbor crews of well over 100 people, maybe many more. It's all a matter of scale. They also might be very automated and carry cargo for drop-off on their first test run. Cyclers rely on minimum energy Hohmann transfer orbits, as they essentially make a single long eccentric loop around the Sun, moving between those two bodies. In the case of the Mars Cycler, it spends 5 months going from Earth up to Mars, spends another 16 months up past Mars, and another 5 months again back down to Earth's orbit, then repeats the process every 26 months. I use the analogy of a big empty train that drives a scenic route and never stops. You still have to expend fuel as normal to get people, equipment, and supplies to and from the cycler. But at least you have a big comfortable living space for the trip once you did, and a lot of heavier equipment and recyclable supplies for those 5-month journeys also need to be brought just once. It is often suggested that we would use 2 Aldrin Cyclers running on different schedules to cut down on trip duration, one used for the trip there and the other for the one back. And even in a more distant future with faster spacecraft propulsion that might use tons of energy to get you to Mars and back in a week or less, which would be great for travelers, you still benefit immensely by moving cargo this way or passengers not in a rush. Timing is still problematic, as usual with launch windows into space, but you can launch early and avoid weather issues by already being in space. Needless to say, you've got a problem if you miss the rendezvous window after that. You could burn more fuel to catch up, the window isn't that tight, but unless you've got a space station to return to at Mars, you are going to have to land again on the red planet. This is one of the reasons I tend to like robust missions, with cyclers and a space station orbiting the planet, and a permanent facility below that you're just changing crew out of, as it means you've got a lot more redundancy and backup plans available. And when you're planning trips of hundreds of millions of miles lasting hundreds of days, you could never have too much redundancy. This approach is not limited to moving between Earth and Mars, it works on any pair of planets. We also say cislunar space and Mars rather than Earth, as it might be carrying traffic from our moon or from various space bases rather than Earth directly. So you can't have an Earth-Venus cycler or an Earth-Saturn cycler or even a Mars-to-Jupiter cycler, where it may be carrying volatiles back from the icy moons of Jupiter for Mars to use in terraforming or paraterraforming operations. Cyclers are great for near the moons of Jupiter, where the radiation around Jupiter is immense, and thus short flights on less shielded shuttles using less fuel to get to a cycler that carries heavier shielding for long trips is ideal. They are also great candidates for nuclear propulsion since they don't need to come particularly near planets and can use ion drives or other low-thrust, high-efficiency engines. Indeed, they could be built to give a little boost to ships leaving them to save them fuel, and then regenerate the momentum they loaned those ships. As an alternative to making or carrying fuel from planets, you could be making it on moons and having those brought into orbital depots or the cyclers themselves to refuel ships. Speaking of moons, the cycler method works as well on 2 moons orbiting a planet as it does 2 planets orbiting a star, or asteroids for that matter. Indeed, we have an interstellar version we looked at in its own episode some years back. Such a cycler castle could make trade among the moons of Jupiter vastly more practical, as the cycles are a lot shorter in duration for lunar transits and that extra shielding is a literal lifesaver. But they could be stocking up ices to hand off to a Jupiter-Mars or Jupiter-Earth cycler, or even a Jupiter asteroid belt cycler, and a nuclear-powered cycler could spend that long trip transmuting those ices into rocket fuel with this extra energy, and replenish its own propellant while it was at it. Indeed, the shipments might come by unmanned pods, rockets or fired from a mass driver from Ganymede or Europa. Those could then be unloaded to depots for the thirsty ships needing water, fuel, air, or whatever else we wish to trade, including surplus food grown on a cycler. In elliptical orbits, you are essentially falling down on the return part of the loop and speeding up as you go, then slowing after you loop around the primary and back out from it, with gravity trying to pull you back. This means that your speed is lower on that boring leg spent out past the more distant of the 2 bodies you're moving traffic between. Thus, you don't really want anyone on there besides a tender crew. We'll talk more about why and how long voyages to other planets would be, along with a quicker version to our own moon, in just a moment. Cyclers spend most of their voyage in dead space. These might be highly automated with the intent to leave the craft empty, except for when it is making a trip between the 2 bodies. Cycler trajectories occur in multiples of the synodic period between those 2 bodies, or when they reach conjunction again. That's how long it takes for them to loop back to the same spot relative to each other. So Earth orbits the Sun considerably faster than Mars does, once every 365 days, versus 587 days for Mars, but has to loop around to catch back up with Mars, which has been moving that whole time. So Earth and Mars both rotate through much more than 360 degrees, and this full synodic period is 780 days, 2.135 years, or 25.6 months, or 111 weeks. Ironically, this is one of the worst options for timing. The next worst is with Venus at 584 days or 1.6 years. Targets in the asteroid belt tend to come in about a year and a half too. Everything else on a cycler orbit for Earth is just over a year because they orbit very slowly, so Earth just needs to loop around a bit over once to catch back up to them. And they will not have completed a full orbit themselves. Mercury, the high-speed planet closest to the Sun, is an exception, with a synodic period of 116 days. And our own moon has a 29.5-day synodic period. A handy point to note, because that's how long between full moons, whereas the moon actually completes an orbit of Earth of 360 degrees every 27.3 days. Earth moves further around the Sun in that time, and so for the moon to get back to its full moon location, exactly on the other side of Earth from the Sun, takes an extra 53 hours. Earth's year being 365 days long, our synodic periods with the outer planets are 399 days for Jupiter, 378 for Saturn, 370 for Uranus, 368 for Neptune, and 367 for Pluto. This does not mean you're making the trip that fast. You still have to orbit further than your target planet is. Thus, you are going to have a total cycle time longer than the outer body's own year, which is 12 Earth years for Jupiter and a couple of centuries for Pluto. You are not necessarily passing very close to the planet each time either. That first launch from Earth, done at the right time, gets you to Mars 5 months later, and then loops back across its orbital path around month 21, but you're nowhere near Mars right then. Indeed, Earth is much closer, and you'll return to it in month 26, and get a return to Mars at month 31. We could potentially be considering powered low-thrust trajectories on that cycle to alter this, and we will in a bit, but it's easier to use a second one that does a fast run from Mars to Earth instead. Normally, when we talk about 26-month launch windows to Mars, it's the same basic concept, though the timing isn't the same. You get there in more like 9 months, land, then launch when the Mars to Earth window arrives, which is a separate schedule but also on a 26-month timeline. So launch from Earth on September 26, 2024 would arrive at Mars on June 11, 2025. Irritatingly, the window from Mars back to Earth opened up July 20, 2024, before we even departed Earth, and would have arrived April 5, 2025. The next window home from Mars isn't until November 11, 2026, with an arrival date of May 24, 2027. So you spend a year and a half waiting for your return window down on Mars. That's a 971-day voyage, 32 months, not counting the time actually getting up from Earth, as you're probably departing Earth some days earlier to avoid risking missing the Martian window from bad weather and getting to a good position to make the burn to your transfer orbit. A second cycler lets us get away with some shorter windows. Now, here's where things shift around a bit, because we don't need to have a period of just one synodic cycle. We aren't planning to ride the thing around all the time, but just for that short leg from one planet to another. So we can get much more frequent windows by having multiple cyclers and ones on different orbital durations, say 2 or 3 synodic periods. We also contemplate grabbing some small asteroid on trajectories not too far off a cycler orbit to shove into one of these, then dig into it and use it for shielding and raw materials. I should note that an Earth-Mars cycler can be set to pass close or through the asteroid belt, so it might serve for missions there too. This is where powered cyclers come into discussion as well. Because while the cool thing about a cycler is that you don't need to constantly burn fuel, if you already have a nuclear reactor in there anyway, you could be running an ion drive, as we already discussed, with that surplus power and just tanking up on new propellant occasionally, as ion drives use a lot less mass of propellant than a chemical rocket does. They just burn real slow. But these cyclers have a surplus of time, especially ones on multiple synodic periods or to deeper space objects beyond the asteroid belt. I should note that a solar-powered one could also do this on legs closer to the Sun, but those are short, so this is an area where nuclear power, be it fission or fusion if you've got it, would tend to work best, though beaming power out by a laser or microwave is also an option. So too, a solar sail or magnetic sail has a lot going for them. Ethan McDonald looked at a powered version of a cycler, assuming a low-thrust option like this a couple years back, and calculates a window that would have left Earth on February 23, 2022, arrive at Mars over a year later in March 7, 2023, departed back to Earth just 1 month later on April 6, 2023, and arrived home on May 20, 2024. This does not leave you a lot of time on Mars, but would be handy if you were swapping crew out on a mission. They get a month to get down to the planet with the new folks and supplies, meet, help accustom the new arrivals to the ongoing projects, and then head home. The other advantage of this powered route is that you are arriving at Mars at 5 km per second relative to Mars, whereas the normal version, also called the ballistic version, involves arriving at Mars from Earth at 11 km per second, and leaving Mars to go back to Earth at 6 km per second. That means your shuttle coming to and from the planet needs to spend a lot more fuel to make its transfer from the planet to the cyclers or vice versa. Either version works best with multiple cyclers on the track, typically 2, but again we can get away with a complementary pair on any of the cycler orbits. Ryan Russell and Cesar Ocampa identified 24 Earth-Mars cyclers with periods of 2 to 4 synodic periods, and even more for larger numbers of synodic periods, along with hundreds of non-ballistic cyclers, ones which would require some powered maneuvers. Since these generally are designed individually for either getting you from Earth to Mars or Mars to Earth, we typically refer to the former as the up escalator and the latter, for the return trip, as the down escalator. An exception to this would be cyclers going to Venus or Mercury, since they would be down from Earth, as the Sun is at the bottom of the solar system, while the Kuiper belt or even the Oort cloud may be thought of as its top. Another exception to the dedicated up and down escalator would be those traveling to the asteroid belt, Kuiper belt, or Oort cloud, as those are not single spots but a wide disk or torus or even sphere, allowing an object passing through them to be having long rendezvous windows to many objects, both coming and going, and with cyclers of different periods. Since in the case of the asteroid belt, orbital periods for asteroids are anywhere from 3 to 6 years. Another modification Aldrin suggested was a semicycler as an alternative to a ballistic or powered cycler. This one arrives at Mars from Earth and enters orbit of it, acting as a base of operations in space during that time, then leaves later for a return trip, and this uses a lot of fuel but takes the fuel load off the shuttles themselves, and various proposed gravity assist maneuvers cut the fuel requirement down by 15%. These are likely to be much less massive affairs than the kind we are imagining that would be on ballistic trajectories for centuries of stops, and instead would be more akin to other notions of having a ship that goes to Mars, stays in orbit, and then departs after the crew go down, explore, and return on some shuttle or lander. Now, as mentioned, these can be set up for other planets, and they are particularly nice for Mercury, where you have a much shorter synodic period, and where powered orbits might be easier with all that sunlight to draw on, particularly for a solar sail. Generally, you get faster speeds involved too. But a much shorter version, and one that might be handy sooner than later, is a cycler to the moon. And this is something Buzz Aldrin and Anthony Geneva explored in a paper a little under a decade back, called a free return Earth-Moon cycler orbit for an interplanetary cruise ship, and reminds us that we don't have to make cyclers between planets around the same star or moons around the same planet, but can set them up with some modification for a planet and its moons, or even Lagrange points. I should note that a lot of folks have worked on cyclers over the years, including Buzz's son Andy Aldrin, and I do not want to diminish their own input, even as we remember Buzz, nor do I want to imply they're only rollers for getting to Mars or even our moon. An Earth to solar L1 cycler might be very handy, for instance, as we often imagine setting up large orbital infrastructure there, especially on other planets where we might want to help terraform them by putting solar shades, lenses, or magnets there to help cool a planet like Venus, or warm one like Mars, or give Mars an artificial magnetosphere to help it retain an atmosphere we might want to add to it. Since there are likely to be a lot more planets in this galaxy that are almost habitable than actually habitable in these regards, many might have robust L1 infrastructure to help make that planet habitable and benefit from a cycler to them, or to their L4 or L5 Lagrange points, as much as a moon cycler, as many may not have a moon of note. We do, and we haven't been back to it in half a century. The youngest person to walk on the moon, Charles Duke, was born in 1935, and I dare say the only reason we have any of those moonwalkers still with us is their overall good health, which was a factor in their selection and made for impressive longevity. An Aldrin Cycler used for the moon could help us get back there and provide a steady trip on a device that can handle the radiation in space. And if we have an established moon base and communication satellites there, there's no need for a command module to orbit the moon while folks are down at a permanent base. Nor do we need the journey to be particularly short. Apollo 11's whole mission was just over 8 days long, from launch to splashdown, and Aldrin and Armstrong spent just over a day on the surface of the moon. As a side note, we'll be coming up on the 100th anniversary of Bob Goddard's first liquid-fueled rocket back in 1926. And not many know that Buzz Aldrin's father, Edwin Eugene Aldrin Sr., studied rocketry under Bob Goddard. Buzz is the junior in this case, and both went by Gene and Buzz respectively. Gene Aldrin was an engineer and physicist and founded the Air Force Institute of Technology at Wright-Patterson Air Force Base in Dayton, which I used to work at in 2000, back when I was 20 and finishing up my undergrad in physics. Back in 1969, when they opened up the Robert Goddard Memorial Library, Buzz Aldrin cut the ribbon for it on its opening day. And when he traveled to the moon later that year, he took with him a miniature version of Goddard's autobiography. NASA told him he couldn't leave it on the moon, so he brought it home, signed it, and gave it to Goddard's widow, Esther. So that book made the whole journey along with the Apollo 11 crew and completed another circle too, for the Goddard and Aldrin families. 3 or 4 days of traveling in a cramped module is no fun, so making that trip longer is unappealing, but a cycle from Earth to the moon doesn't make that much longer unless you're crewing the device continuously, which I suspect you would be, and could be made a lot more comfortable by bigger size, again including more shielding and perhaps a spin gravity section somewhere between the moon and Earth gravity for people to adjust to. It might be a popular cruise route too, as some of its legs go out from Earth and back to Earth without passing the moon in the middle. Its orbital patterns look more like flower petals extending out from Earth than the elliptical version around the Sun of planetary cyclers, and the 3-petal cycler that Aldrin suggested in 1985 for a cycler to the moon makes a pass at the moon every 26 days, but Earth more often. It's basically flying by Earth on each of those petals, but only one petal goes to the moon, and the other's in an empty space. Each leg lasts around a week, again a good cruise length, for possible space tourism to help fund its primary mission back and forth to the moon. Aaron Storff originally suggested a lunar cycler concept of 4 petals back in 1963, which has longer transfer times, and actually requires a little bit less thrust than the later 3-petal design at 19 meters per second of delta V, but neither is very high, tens of meters per second, not kilometers per second, so we can replenish that a lot easier. There are several other patterns potentially available, and if we do build up our lunar L4 and L5 Lagrange points, which are attractive space development locations too, a low-powered version might be able to rendezvous with one or both of them on an empty loop. People traveling to and from the moon spend a few days on each leg, and those departures occur a little under once a month, and multiple cyclers could narrow that down even more so that if we wanted we could have daily departures, but just one can do the job well enough for all purposes, so we can be bringing crew and supplies to a permanent moon base much more often, and other versions designed to function with a lunar space station or a lunar space elevator open other doors. And there we have it, a way to get back to the moon or to other planets, developed with the assistance of one of its very first pioneers. A vision from a man who not just walked on the moon, but has spent his life helping others follow in those footsteps, reaching for new worlds beyond.